The non-Abelian gauge theory contains the non-commuting generators in the Lie algebra, and this makes eventually the self-interaction term of the gauge boson in the Lagrangian, and also gives the negative beta function, which makes the asymptotic freedom behavior still in the renormalization. So today I will talk about the non-Abelian gauge theory in detail. This is a revision on this topic in the 2 or 3 years. So the in the standard model, the typical non-Abelian gauge theories that comes from the Lie algebra, like as SUN. The generators of these Lie algebras that do not commute with each other. So the commutator relation satisfies the following form, where the F represents a structured constant, and the T is the generators of the Lie algebra. And we can represent these generators with some specific matrix, such a representation function denoted as the capital R. And in the Borasiu, there are two well-known representations. The first one is the fundamental representation, which is the generators represented by the n by n matrix. And there are also the adjoint representation, which use the structured constant. Before going to our non-Abelian gauge theory, let's talk about some structures and the fundamental quantities in the Lie algebra. First of all, we can normalize the generators by defining the thinking index TR. The traces of the multiplication of the two generators can be normalized by the thinking index TR. For the fundamental representation, when R equal to the fundamental, this thinking index becomes a 1/2. And also we can define the quadratic Casimir C for some specific representation like that. And so there are two quantities. The first one is the thinking index TR, and the quadratic Casimir CR. And because there are two different types of the representation, the first one is the fundamental, and the other one is adjoint. And we already know that the TF is 1/2, and for the adjoint representation, the thinking index is given by the capital N, and for the quadratic Casimir, the fundamental representation, this is given by the n squared minus 1 over the 2n, and the adjoint, for the adjoint representation, this is given by the n. This can be obtained by some relation between the TR and the CR, but I will keep it here. And these constants are the very important and fundamental quantities in the Lie algebra. And this will be turns out again when we calculate the sample text in the QCD. Now I will construct the non-Abelian gauge theory. This is called the Yang-Mills Lagrangian. We can introduce the gauge field by constructing three generators A mu. And for covariance with the gauge symmetry, one can define the covariant derivative d mu in terms of like that. And the commutator relations of the covariant derivatives gives the Weierstrass F menu. So if we calculate this Weierstrass F menu, the full expansions includes the coupling term between the two gauge boson. This last term only arises from the non-Abelian theory. In the Abelian gauge theory, like the U1 symmetry, there is no such a term. And this term makes the self-interactions of the gauge boson, and also the gauge bosons get the specific charges. So we want to make the theories, the invariance under the local gauge transformation the transformations of the real algebra can be expressed by the exponential form. For the matrix spinor build psi, this is transforms like the following form. And also we want to make the covariant derivative d mu's also the transforms under the such a real algebra. And so if we consider that the d mu psi, this is the transforms as u acting on the d mu psi. So to satisfy this condition, the covariant derivative d mu satisfies the following transformation rule, so that the UR psi, so that this UR inverse and UR can be offset each other. So we can expand this requirement for the right hand side and the left hand side. And just calculating step term by term. And we can compare the left hand side and the right hand side. So the transformation rule of the gauge field A mu can be obtained. So the A mu prime is given by the following form. Just step by step. And we can expand these transformations, this exponential form, with infinitesimal parameters. So UR is given by the 1 plus I alpha, and the UR inverse is given by the 1 minus I alpha. And alpha contains the its generators. So the first term can expand this as the following one, and the order of the alpha squares the ignorance, and also for the second term here. So the difference between the A mu prime and the A mu so represented by the following form. And the last term can be rewritten with the component part, because alpha contains the TAR and A mu also contains the TBR, but in this case the index are given by the B and C. And by using the commutator relation of the two generators, we can obtain the expression for the last term with the fully component index A and B and C. So the result of the transformation rule of the gauge field A mu is the following. And we can define the this term again as a covariant derivative. Similarly, we can obtain the transformation rule for the Bird-Strong's F mu. Here we know the transformation rule of the covariant derivative, so just insert here, and this is given like that. So the Bird-Strong transform as covariantly in the adjoint representation. Again, also we can represent the infinitesimal transformations with the component field. So now we can construct the gauge invariant Yang-Mills Lagrangian, because the Bird-Strong's F mu transforms like such a form, very simple form, unlike the gauge field of A mu. So we can just written the gauge invariant Lagrangians in terms of the F mu and F mu. This is called the Yang-Mills Lagrangian. And we can add the Dirac fermion with the covariant derivative. And if we expand the first term, the kinetic term of the field strength or gauge field A mu, then we can obtain the cubic or quartic term, self-interactions of the gauge boson. So this is a typical common terms, the same ones with the abelian gauge theory, but in the second slide and the third line there are quartic interaction like that, but there are the kinetic term and also the quadratic interactions through the A mu. So this is a very important features of the Yang-Mills theory based on the non-abelian gauge theory, self-interactions of the gauge boson. So now we construct the Lagrangian of the theory. The next step is the computing the amplitude. And this is contains the one loop gauge boson, so we need to fix the specific gauge. Similar to the Non-Abelian gauge theory, we can also adopt the R gauges and also the gauge fixing terms like that. So the Cauchy's represented some specific gauge choices. So the Coulomb propagators, the Coulomb means that the gauge fields I mu in the QCD can be represented like that. And also for the Bellman propagator, this is the same to the U1 theory. And the Bellman gluon vertex, now this includes the generators. And also there's a gauge self-interaction, gauge boson self-interaction. So 3 gluon vertex and the 4 gluon vertex is important for Bellman law. So here is a 3 gluon vertex. Because it contains the derivatives terms, so this gives the momentums and the 4 gluon vertex. And the important features is that these self-interactions of gauge bosons includes the structures constant. So in also the Bellman rule, there's the F, A, B, C and their permutations. And I will turn to the additional contributions. In the non-Abelian gauge theory, this requires the Bada-Poop's ghost for the unitarity. For the path integral formalism, we can evaluate the generating functions by using the path integrals with the given Yang-Mills Lagrangian. And one can fix the gauge's choice for the gauge field. This gauge condition can be represented by the GA through the I. For example, the GA can be given by the partial mu A mu. And this delta functions includes the gauge choices. And to give the normalizations, there's the prefactors, which is represented by the Bada-Poop's determinant as a Jacobian form. And this Bada-Poop determinant can be represented by the exponential form by introducing the anti-commutating scalar field. Even though this is a scalar field, this C and C bar, they satisfy the anti-commutativities like the Grassmann number. So why does such a Bada-Poop's ghost such a new fields are necessary? So the reason why is because under the gauge transformation, all fields are related to the same gauges orbit. So we should remove such gauges to freedom by fixing conditions. So for the gauge fixed Lagrangian, there's additional terms like the Grassmann number, like Bada-Poop's ghost. This ghost is not the physical state. This only appears in the internal line, and we cannot observe this ghost field, but contributes via the loop level. Also, we can release the ghost propagator from the gauge fixing Lagrangian, and also the interaction between the ghost fields and the gluon, because this covariant derivative d mu contains the gluon field. So the gluon and the ghost vertex is the givens like that, but there's the derivatives term, also the momentums that appears again. The ghost loop contribution is the importance when we calculate the gluon self-energy. So now we construct the Lagrangians and the Boole-Bellman rule. The remaining part is just calculating the self-analysis diagram. The learning of the gauge coupling can be obtained by the normalizations of the gluon self-analysis. The gluon self-analysis contains many loop contributions. First of all, here's the gluon, and because there are two gluon vortices like that, and also the four gluon contributions like that, and also the ghosts coupled to the gluon like that, and finally the fermions coupled to the gluon field. So these four diagrams all coupled to the ghost, the gluon. So that contributes to the gluon self-analysis. And now we need to the some fundamental quantities coming from the real algebra. Because for the first part and the second part, the self-analysis, the self-interactions of the gauge boson contains the structured constant FABC, and also the gauss gluon vortex you can check here, and also the insides of this. So the first three contains the structure's constant, and by definition of the so these adjoint representations, in the adjoint representation, the generator is given by the structure's constant. So FA, BC, so the BC is a matrix index, and the FA is represented some specific generator. So that this gives some Casimir, quadratic Casimir string adjoint representation. And for the final one here, the interaction between the gluon and the fermion field, because this vertex only includes the generators in the representations of with the fundamentals one. So this gives the linking index. So the all the loop contribution can be represented by the quadratic Casimir string in the adjoint representations and the linking index. So by calculating this loop diagram with some complicated calculation stuff, there might be some divergence behaviors if we use a code of regularizations of the dimensional regularization, and to remove this divergence we need to add some specific count term, and eventually this makes the learning of the coupling over some specific scale of the mu. So one can evaluate the beta function which represent the learning coupling, and this learning coupling so can be decomposed from the contributions with the quadratic Casimir's of the adjoint representations and the linking index, and also the number of the labels is important. So the QCD has the SUN graph, SUN C groups, whereas the NC represents the number of the color. So the TR and the TF are equal to the 1/2, and the quadratic Casimir in the adjoint representations given by the NC. So the these coefficients in the beta function, the beta zeros can be represented by the NC, the number of the colors, and NF, the number of the fermion. If this beta zeros is a positive, which means that the beta function is negative with this minus sign, so that this makes the asymptotic free. So if we plot the g over the mu, it behaves like that. The slope represents the beta function, and this is negative. One, this beta zero is a positive. This positive beta zeros is realized when n up is smaller than n c. And in the typical QCD, n c is given by the 3, and then maybe the n up is given by the, I remember that this is just a 3 also. So that this condition is satisfied, so the beta function is negative eventually, and so the coupling G becomes small in the energy limit. So this is called the asymptotic tree. This means that for the high energy, or the distance become very small in the UV limit, the coupling becomes extremely small. But in the opposite limit, when the energy scale becomes small and also distance is quite large, then the coupling becomes extremely increases. This makes a color confinement. So this is the reason why the QCD calculations are very hard, because at some moment G touches the number 1, and this makes the perturbative expansions is ruined. We can solve these algebra functions with the logarithms forms in terms of the alpha s rather than the comparing this alpha s is the Barnes-Stokes constant form, and the alpha s shows that such logarithms are solutions. So again, this represents the color confinement and the asymptotic freedom. So when the mu go to the ultra UV limits, then the coupling becomes small, so the perturbation works very well. But when the mu goes to the IR limit, then the coupling scales and the perturbation theory breaks down. So why there is such a non-Abelian gauge theory contains the different behaviors of QED, because in the QED the coupling constant behaves like that. So this is for the QED in the IR limits, the coupling is small, so this is called IR free, and for the higher the scale, the coupling is divergent. This is called the lambda 4 at some specific scale, but the extremely very large. So qualitatively, with some specific intuitions, because the gluon-sulfur interactions makes the anti-screening. So if we consider some R charges from the colorless gauge symmetry, then the dipole moment of these color charges makes by the opposite direction. For the electric charges, the background polarizations makes the electric dipoles by skewing the effects of these positive charges in the center. So this background polarization screen the effects of this plus. So in the far distance, the electric fields are decomposed as the one of the R scale, and this is the reason why the QED show that the IR free. IR means that the energy is extremely small, and the distance is extremely large, then the coupling becomes increasing behavior. But oppositely, the QCD show that anti-screening. So the effect of this color charges in the centers increases when the distance becomes large. So this makes the wide the independence precork cannot be observed, rather than that the single precork we can only observe the bound state like the baryon and the meson, or the so-called hadron. But in the high temperatures above the QCD scale 100 MeV, and the scale is very large, so the coupling can decrease along the learning behavior, and this makes the cork gluon plasma. So today we talk about the non-Abelian gauge theory, starting from the real algebra informations and turning to the constructing the Young-Mills theory, Young-Mills Lagrangians, by satisfying the transformation rule of the covariant derivatives, gauge Beer strengths, and we can write the Weimar rule for the gluon, fermion, and additional Vatopavlov's ghost. And eventually we can calculate the beta functions to check the learning behaviors of the coupling. And the important characteristic of the non-Abelian gauge theory, especially QCD, show that the asymptotic freedoms are in the high energy, but in the higher limits, they show that the color confinement, so the coupling becomes rather than the one, and the perturbation theory can break down. And this is a very important feature for the QCD to represent the bound state, not a single free quark.